Hello, welcome to another module in this massive open online course. So we are looking at various aspects of information theory, and we have also defined the concept of entropy, correct? And we have seen various properties of the entropy of a source, which we said characterizes the average information or also the average uncertainty associated with the source, the average information per symbol of a source or the average uncertainty that is associated with the source. All right, so let us now look at an example to understand this better. Okay, so I want to look at an example for entropies, correct? So let us consider a binary source implies the source alphabet has two symbols similar to 0 and 1, okay, a digital source. Source alphabet has two symbols, so I can say S equals S0 and S1. These are the two symbols of the source, correct? So remember, this is the source alphabet. These are the two symbols which you call the source alphabet. This set is known as the source alphabet. Let probability of the symbol S0 be P, then naturally probability of symbol S1 equals 1 minus P. All right. So therefore the entropy H of S is, well, P naught, or basically let me elaborate this, that is probability of S0 log to the base 2 1 over probability of S0 plus probability of S1 log to the base 2 1 over the probability of S1, okay, which is basically nothing but P times log to the base 2 1 over P plus 1 minus P log to the base 2 1 over 1 minus P. Okay, this is your H of S, which is the entropy of the binary source, and this quantity is also known as H of P. Okay, this quantity P times log to the base 2 1 over P plus 1 minus P times log to the base 2 1 over 1 minus P, this is also denoted by H of P. So alright, so this is basically the entropy of the source. Or rather we can say entropy of our binary source. Okay, entropy of the binary source. And now you will also see the first property. So we have derived the entropy of the binary source as P times log to the base 2 1 over P plus 1 minus P log to the base 2 1 over 1 minus P. Now you will also realize that for the first property is that you will see that H of P, we have denoted this by H of P. H of P is equal to H of 1 minus P. So you have H of 1 minus P. Naturally you can see H of 1 minus P is 1 minus P log to the base 2 1 over 1 minus P plus 1 minus p log to the base 2 1 over 1 minus p, which is again you can see 1 minus p log to the base 2 1 over 1 minus p plus 1 minus p is p log to the base 2 1 over p. Okay, so this is your quantity h of p. So h of 1 minus p, so we have h of 1 minus p equals h of p, that is a property. And this is natural because we have seen that it only depends on the probabilities, right? It does not depend on the actual symbol. So if we have a binary source with the probabilities given by p, that is one of the symbols has probability p, the other has probability 1 minus p, it has the same information as where the first symbol has probability 1 minus p and the other symbol has probability p, because we said it only depends on the probability, the combination of probabilities. It does not depend on the symbols, the information does not depend on the symbols themselves. Okay, it depends only on the probabilities with which they occur. Okay, now also observe that limit p tending to 0 of h of p, this is equal to, well, limit p tending to 0 p log to the base 2 1 over p plus 1 minus p log to the base 2 1 over 1 minus p. Now as p tends to 0, 1 minus p, this becomes 1 over 1 minus p, this becomes 1. So this tends to, this is equal to, well, limit p tends to 0 of p log to the base 2 1 over p plus, I can substitute 1, so 1 log to the base 2 of 1, this quantity is 0. We know, we have previously derived that this quantity, limit p tends to 0 p log to the base 2 1 over p, this is equal to 0. So overall this quantity equal to 0. So limit p tending to 0 h of p is 0, we know. So at p equal to 0, so limit p tends, as p tends to 0, h of p tends to 0, correct. So we have limit p tends to, similarly we have h of p equals h of 1 minus p. Okay, we use the property h of p equals h of 1 minus p, which now, from which it now follows that limit p tend to 1, correct. So now it naturally follows that limit p tending to 1 of h of p is also equal to, well, this is equal to, since h of p is h of 1 minus p, equals limit p tending to 1 of h of 1 minus p equals limit p tending to 0 of h of p, this is equal to 0. Okay, so because if p tends to 1, correct, if p tends to 1, then 1 minus p tends to 0. Okay, so which means that limit p tends to 1, h of p is also equal to 0. So what you see is something very interesting. When either p equal to 0 or p equal to 1, that is, if the probability of 0, is equal to 0 or the probability of 0 is equal to 1. Okay, let us look at these two scenarios. So, H P equal to 0 implies probability of S of 0, probability of S of 0 equal to 0, probability of S of 1 is equal to 1, which implies that source always generates symbol S1, because probability of S of 0 equals 0. So, source always generates S1. On the other hand, if P equal to 1, this implies probability of S of 0 equal to 1, probability of S of 1 equal to 0. This implies that source always generates the symbol S0. So, in either of these two cases, when the source always generates S0 or source always generates S1, that is P equal to 0 or that is P equal to 0 or P equal to 1. Okay, the uncertainty is 0 because the source is always generating either S0 or S1. So, there is no information in the source, because we know the next symbol the source is always going to generate is going to be either S0, right, if P equal to 1, because with probability 1 it generates S0, if P equal to 0 with probability 1 it generates S1. So, there is no uncertainty, right, the source is always generating either one symbol or the other, and hence the information, right, since there is no uncertainty, right, the information associated with the source, the entropy, the average information per symbol associated with the source is 0. Since we know with certainty that the source is going to, if P equal to 0 with certainty the source is generating S1, if P equal to 1 with certainty the source is generating S0. Okay. Now, let us look at when does the maximum entropy occur, or when does the maximum average information per symbol occur for the source. Okay. So, in both these cases P equal to 0, in both these cases there is no uncertainty. This implies no information, or that information content is 0. Okay, implies the average information per symbol is equal to 0. Now, consider again h of p equals p log to the base 2 1 over p plus 1 minus p log to the base 2 1 over 1 minus p. Okay. Now, to find the maximum, let us differentiate this with respect to p. To find maximum, let us differentiate with respect to p. So, h prime of p, the derivative, that is d over dp of hp, well, that is p log 2 to the base 1 minus, that is basically you can write it as d over dp of minus p log to the base 2 p minus 1 over p minus 1 minus p log to the base 2 1 minus p. When you differentiate it, of course derivative with respect to p is 1, so this is minus log to the base 2p plus when you differentiate it with respect to the log 2p, so I'm using the chain rule, minus p log to the base 2 of p, that can be written as well. I can write this as log p to the base e, that is a natural logarithm, times log e to the base 2, so that is minus p times, well, log p to the base e, if you differentiate it, that becomes 1 over p times log e to the base 2, correct. Similarly, this is minus derivative of 1 minus p is 1, so 1 minus p is minus 1, so this becomes plus log 2 to the base 1 minus p, and what we finally left with is minus 1 minus p, derivative of log to the base 2 1 minus p is minus 1 over 1 minus p times log e to the base 2, which is equal to, well, minus, well, that will become minus log 2 to the base p minus log e to the base 2 plus log to the base 2 1 minus p plus log to the base, so you cancel these and what we get is minus log to the base minus log p to the base 2 plus log 1 minus p to the base 2. Now if you equate this to 0, to find, so differentiate and equate to 0 to find maximum, and this implies that basically log 2 to the base 1 minus p over p equal to 0, which implies 1 minus p over p equal to 1, which implies 1 minus p equals p, which naturally implies p equal to half. So we get that the entropy is maximum for p equal to half. That is when both the symbols, that is S0, both the symbols S0 and S1 of this binary source have equal probability, then the entropy is maximum. So we have entropy is maximum for probability S0 equals probability S1 equals 1/2. And you can also see that this is the maximum, because if you differentiate it again, h double prime of p, that will be, well, h prime of p we have, that is derivative of h prime of p, that is the derivative of, well, minus log to the base 2 minus log p to the base 2 plus log minus p to the base 2, which is equal to, if you take log e to the base 2 common, this will be minus 1 over p minus 1 over 1 minus p. So this is minus log e to the base 2 1 over p plus 1 minus p, which is clearly less than or equal to 0. Second derivative less than or equal to 0 implies there is a maximum at this quantity. Remember, p is greater than or equal to 0. 1 minus p is greater than or equal to 0, therefore this quantity is less than or equal to, because of the negative sign it is less than or equal to 0, implying that indeed at p equal to half there is a maximum, the entropy reaches its maximum. And what is the entropy at p equal to half? H of p equal to half, or rather h of half equals half log to the base 2 1 over half, that is 2, plus 1 minus p, that is half log to the base 2 1 over 1 minus p, that is 1 over half, that is 2. Log to the base 2 is log to the base 2 of 2 is 1, so this is simply half plus half equals 1. So h of half so if you observe, this is something very interesting. So h of half equal to 1, which means this is 1 bit. 1 bit per symbol. Okay, this is 1 bit, which means h of half equal to 1. This is 1 bit per symbol, and we have already seen that h of 0, that is limit p tends to 0, p tends to 1. If we denote them by h of 0 and h of 1, they are 0. Okay, and it reaches maximum at p equal to half. So if we plot this, entropy, you will realize that it looks something like this. Okay, so this is on the x axis we have p, on the y axis we have h of p. So this is p equal to 0, this is p equal to 1, and we have this it reaches its maximum, that is at half it is equal to 1. So it starts from 0, goes all the way up to 1 at p equal to half. So it's something like this. It's not pointed, in fact its derivative at half is 0, which is what I'm trying to show approximately. So this is how it looks like. Okay, so at half it reaches its maximum, that is maximum equal to 1 at p equal to half. This implies that here this is in fact 1 bit per symbol, correct? So at all these points, for instance, if you look at this point, this is less than 1, this implies it can be represented with lower number of, so we have two symbols 0 and 1. What this means is the average entropy is less than 1, implies that it can be represented with less number of bits per symbol than 1. Of course, when p equal to half, it implies that you need on an average 1 bit per symbol to represent this. And when entropy is less than 1, for instance when p equal to 3 by 4, correct, entropy is less than 1, you can see that it requires less than 1 bit per symbol on an average to represent this. Alright, and that's what we are going to see as we progress to the rest of this course. Okay, so for instance, less than 1 implies lower than 1 symbol can be represented using less than, so implies can be represented and this is what the encoding process does, right? The encoding process expected to do is take these source symbols and come up with an efficient code, come up with an efficient stream, right, an information bit stream to represent this using the minimum number of bits, right? Take two binary symbols S0 and S1, correct, S0 and S1, and come up with an information bit stream to represent this efficiently using the least number of possible bits, that is the lowest possible bits in an average sense, that is the average number of bits used to represent each symbol must be the smallest. Okay, and that's what we are going to, this process is termed as coding or encoding. In fact, that's the theory regarding this is what we are going to look at in detail as we go through the rest of the modules of this course. Okay, so basically that's what we have seen. We have seen an interesting example of a binary source with two symbols S0 and S1, probabilities P and 1 minus P. We have looked at what happens at the extremes, that is P equal to 0, P equal to 1. There is no uncertainty, the information is 0. Maximum information or entropy occurs at P equal to half, and of course if you plot it, it looks like a nice concave function which starts from 0 at P equal to 0, rises to 1 at P equal to half, and falls down again to 0 at P equal to 1. Okay, alright, so we'll stop here and look at explore other aspects, other properties, study this behavior of entropy further in the subsequent modules.